On February 19, 2026, a small Canadian startup put a chatbot on the web. You typed a question. It answered so quickly that watching the words arrive stopped making sense. An EE Times reporter tried it. The demo cleared 15,000 tokens a second. Taalas's own chart reached 16,960. That number needs a translation. At 16,960 tokens a second, 1,000 generated tokens take about 59 milliseconds. In English, 1,000 tokens is roughly 750 words, a full page of text, before a human eye has properly moved to the next word. It was not a new model. It was Meta's 2-year-old Llama 3.18b, and it was not running on a GPU. Taalas had put that model into the chip itself. The story is not that a startup made a chatbot type absurdly fast. The story is what they had to give up to do it, and why that sacrifice may be exactly what some AI products need. The company was Taalas. It had been founded in 2023 by people with backgrounds at chip companies, including Tenstorrent, AMD, and Nvidia. Its first public machine was called HC1. When it launched, the claim sounded like a category error. The product page said that HC1 could run Llama 3118B at 17,000 tokens per second per user. The chart put an Nvidia H200 at 200, Groq around 600, and Cerebras near 2000 on the same model. One request shape, and a 16,960 token result against 2,000 on the H200 baseline. That was why the story traveled. A 24-person startup said it had made a single user see text nearly 10 times faster than the previous specialist leader. And there was a real board, a real server, and a public demo. The HC1 chip used TSMC's 6-nanometer process. It was 805 square millimeters, 53 billion transistors, and roughly 250 watts per card. 10 cards made the 2.5 kilowatt server Taalas listed on its product page. So, number 1. This was not a slide deck benchmark. An outside reporter reached more than 15,000 tokens a second on the demo, but that only made the next question sharper. How can a small team make an old 8 billion parameter model feel faster than systems built by the largest chip company in the world? To see the trick, start with what normally happens when a language model writes one word. A GPU is a general-purpose machine. It can train a model in the morning, render an image in the afternoon, and run a different model at night. That flexibility is why GPUs run AI, but it creates attacks during inference. For every new token, the machine has to work through the model's weights again. Those weights are huge. Moving them from high bandwidth memory to the arithmetic units costs time and energy. For text generation, this movement often matters more than the arithmetic itself. Think of a restaurant with a brilliant chef and one impossible rule. Every time an order needs a new ingredient, the chef must send someone back to a warehouse across town. The kitchen is fast. The delivery route is not. GPU companies have spent years making that route wider. Faster memory, more bandwidth, advanced packaging, bigger racks, liquid cooling. Taalas walked in and made a much more radical proposal. Here is the part that changes the whole picture. What if the ingredients were no longer delivered at all? Taalas did not load Llama into memory every time it ran. It turned Llama's fixed weights and data flow into part of the silicon design. The company changed 2 custom metal mask layers to adapt the chip to a model. On HC1, the base weights lived on the chip in a mask, ROM-based fabric. A programmable SRAM held the pieces that still had to change, including the KV cache and some fine-tuning data. That is the leap. In a normal GPU, the model is software. You download it, load it, replace it, update it. In HC1, the model's core was physical. The paths that normally fetch weights were replaced by paths already built into the chip. That is why the phrase hardwired Llama was more than marketing. The model was no longer just something the computer ran. For its fixed base weights, it was part of what the computer was. This is also why the speed is believable. Taalas did not invent a miraculous way to calculate every token. It removed a large part of the journey before each calculation. The company called this extreme specialization. EE Times used the same phrase, and it is exactly right. HC1 was not trying to be a better Swiss Army knife. It was trying to be a machine that did one movement so well that the rest of the industry looked slow. Which brings us to number 2. The extraordinary speed was not a free upgrade. It was bought by making a chip that knew in advance which model it would run. Here is where that speed starts to matter. At first, 17,000 tokens a second sounds wasteful. Humans do not read that fast. A fast chatbot already feels instant at a few dozen tokens a second. That is true. For ordinary chat, much of HC1's speed is invisible, but the user is not always the thing waiting. An AI agent may call a model, inspect the answer, call a tool, read the result, and call the model again. Repeat that loop 10 times and a 1-second pause becomes 10 seconds. Repeat it 100 times and a product that looked intelligent starts to feel broken. Now, take the same loop and cut generation from seconds to milliseconds. The system can span more tokens, reasoning, compare several candidate answers, or run a chain of small agents without asking a person to stare at a loading indicator. That was the promise analysts saw in HC1. Ketchup's Antoine, writing after the launch, argued that a reasoning model could become interactive if its hidden work took less than a second. That does not make the model smarter. It makes waiting less expensive. The same applies to voice systems. A spoken assistant needs speech recognition, retrieval, a model response, and text to speech inside one conversation turn. If one piece consumes almost no time, the rest of the pipeline gets room to breathe. So this was not really a story about faster typing. It was a story about moving the latency budget somewhere more useful. The next thing is what that shortcut cost. The same decision that made HC1 astonishing also made it fragile. Number 3. HC1 only ran Llama 3.1 API. That was not an incidental limitation. It was the business model. If a customer wanted Quen, Gemma, Mistral, a new Llama, or a model that had not been released yet, a GPU could load it. HC1 could not. Taalas said it could make a new model-specific chip in about 2 months by changing those mask layers. 2 months is impressive for silicon, against a market where a better model can appear over a weekend. It is still an eternity. Lubisa Bajic, Taalas's chief executive, said the company knew this was massively risky. He was right. The moment the fixed model looks old, the extraordinary machine built around it inherits that age. Then there was precision. Taalas's first silicon Llama mixed 3-bit and 6-bit parameters. Taalas itself said this introduced some quality degradation compared with GPU benchmarks. That sentence matters more than the headline number. Quantization is not a trick or a scandal. It is how models become cheap enough to deploy. Fewer bits mean less memory, less movement, and often more speed. But 3-bit formats make a harder trade than 4-bit or 8-bit ones. A 2026 study of Llama 3.18b found that its most aggressive 3-bit configurations delivered the largest average quality drop across its benchmark suite. So HC1's result was not the same Llama, only faster. It was a specific, lower precision Llama running on a dedicated machine. That may be perfectly acceptable for a stable task. It may be unacceptable for reasoning, code, long contexts, or a workflow where one wrong answer triggers a costly action. The product needs to be tested on the job, not just timed on the token stream. And now, the layer this idea had to survive. Here is where this becomes bigger than one Llama demo. The traditional view of AI hardware was simple. Models change too quickly to build a chip around each one. Build flexible GPUs instead. Pay more per token, but stay ready for whatever arrives next. HC1 challenged that view. It asked a different question. What if some models stop changing before the hardware does? Many business workloads do. A company may settle on one support model, one document pipeline, one translation system, or one constrained internal assistant. If its quality is good enough and its prompts are stable, flexibility becomes an insurance policy it pays for every time it generates a token. That is where hardwired silicon could win, not on a laptop. HC1 was a data center product, not as a replacement for training clusters. Taalas was not training Llama. It was serving a model that had already been trained. The future, then, is not a world with no GPUs. It is a split. GPUs remain the laboratory. They train new models, test new ideas, and run the fast-changing frontier. Specialized silicon takes over only after a model is trusted enough to become infrastructure. Paresh Karia, Taalas's vice president of product, described HC1 as a way to prove the architecture before moving to larger models. That next step is the hard one. HC1 fit an 8 billion parameter model on one chip. Larger models need more chips, more coordination, and eventually some of the data movement that the first demonstration escaped. Taalas said a future design could raise density to about 20 billion parameters per chip in 4-bit format. That was a projection, not a product result. The real test was whether the company could scale the model without scaling away the advantage. So what happened? Taalas took Llama 3.1 AB, accepted a lower precision version of it, and built the model's base weights into a chip. That removed much of the memory traffic that normally slows text generation. A public demo then showed that the result was not theoretical. It crossed 15,000 tokens a second in an outside test. What did it mean? For 59 milliseconds, 1,000 token answer stopped being a wait. That does not transform ordinary chat. It can transform systems that need many model calls before a person can act. What made it a real achievement was also its limit. HC1 did not beat GPUs by doing everything a GPU does. It won by refusing to do almost everything else. That is why this was neither an Nvidia killer nor a gimmick. It was a proof that the model hardware boundary can move. A model can become stable enough, cheap enough, and valuable enough to deserve its own machine. It was speed against flexibility, made physical. What would make the case stronger is not another giant token number. It is an independent report on a larger model, quality against the original model, latency at real concurrency, power per accepted task, total cost, and the time required to move to the next model when the old one is no longer good enough. If those numbers hold, Taalas's idea could make AI feel less like a remote service waiting on a data center and more like a component that simply responds. That is the video.